and now I'm going to get rid of those, or try to get rid of those in the next step. By saying, okay, here I'm saying that for all x px holds, so far I had no idea about my domain, but now I have introduced this auxiliary constant. If for all x px holds, then certainly also for a px should hold. So I can just fill in a for that x and see what happens. And the same trick applies to the other formula, which is also universally quantified. You can say, okay, let's just try out the value, the constant a for that x. So now I'm suddenly got rid of all my quantifiers and can continue using the rules that I already knew from propositional logic. Which means that this actually splits, right? This is an implication without negation, so you have to split. And I think you either get not PA, or, so this negation of the first operand, or you get QA, the second operand positively, and the rest always also sticks around. So now branch, and one branch says not PA, PA, not QA, and the other says QA, PA, not QA, and both of them close. And now I'm done. My semantic tableau is closed. Which means that the formula I started with is unsatisfiable. And so the formula this is negation of the other formula, which therefore is valid. So, I did two tricks. One trick to get rid of the negated universal here. There I said, I'm going to introduce a new constant. Just introduce a new name and fill that in for the x over there. And the second trick was to get rid of the non-negated universal quantifiers by taking that new constant that I just introduced and fitting it in for x. And because my tableau now closes, I have established the unsatisfiability of my original formula. That's the basic idea here, and that's essentially how we extend this semantic tableau method to predicate logic. There are, however, several caveats, things to watch. It's also on the slide, so you can read it at leisure. And let's also observe that it is indeed the case that universal quantification distributes over implication. So you should have expected, when you raised your hand, you should have expected that the formula you started with was unsatisfiable. In other words, the thing that is wrapped in the negation was indeed valid. So I proved something that indeed holds, which is a relief. I'm going to do another one. This is the, well, if we forget about the outer implication and the outer negation again, this says that universal quantification distributes over disjunction. Is that the case?
No, I don't think so.
No. I mean, think again of the even and odd numbers. Left-hand side says for all numbers, the number is even or the number is odd, and that is correct. Whereas the right-hand side says for all numbers, the number is even, or for all numbers, the number is odd, which certainly is not correct. So the negation of that formula is therefore should not be unsatisfiable. Yeah, we are negating a formula that is not valid, so the negation should not be unsatisfiable. So let's look what comes out if we try to apply the semantic tableau method to that formula. I'm just going to replace the negation here by or, and that is then the formula we're working with. So first step still the same. worked. First step is still the same. We are getting for all x, px or qx, comma, not for all x, px, or for all x, qx, which can again be decomposed using the rule for a negated OR. So we get for all x, px, or qx, then not for all x, px, and not for all x, qx. Well, what do we do now?
Replace x with a constant?
We replace x with a constant. Yes, that was the way to get rid of the negated universal. So this one stays for the moment for all x, px, or qx. Then we introduce a constant, call it a again for pa.
Not. Should be not pa.
Not pa, yes, that's right. What about this formula over here? Let's do two things at the same time.
Well, it can be either the same or it can be a different one. So you get two branches or
Yes,
a different
that's a good remark. So let's look what happens if we just insert the same constant there. Not saying this is correct. Let's just see what happens if I do this. Then the next step would be to insert for this x over here that new constant a. That's what I did before. So then I get PA or QA, not PA, not QA, which branches because of the or, and I'm stuck with PA, not PA, QA on one hand, and QA, not PA, sorry, this should be not QA, not PA, and not QA. Which closes? Now, I started out by saying you agreed with me that universal does not distribute over OR, so the negation of that should not be unsatisfiable. I just appear to have shown it to be unsatisfiable. There must be something wrong. Yeah, and the something that is wrong is actually what Thies already said. Here I blindly inserted the A for the x in not for all x qx. And apparently that was wrong. And if you think about it, you can realize that it's wrong, or that it can go wrong, because this one says there must at least be one individual for which not px holds. This one says there must be at least one individual for which not qx holds. But who knows if they're the same individual or not? You don't know if they're the same individual. So there's no reason to think that you should insert the same constant both cases. Yeah? So instead you can choose, and that is the correct way, you can choose to introduce a new constant, not QB, and work with that. But that means that when I instantiate the x in the universal quantification for all x, px, or qx, I have a choice. I can say, let's try out A. I can also say, let's try out B. And because it should be true for all x, in fact, I can try out both of them. Yeah? So let's do that. So now it goes differently. I get a larger formula saying PA or QA, where I instantiated x with A, PB or QB, where I instantiated x with B, and of course not PA and also not QA. This is now what I have.
QB, right?
QB, sorry. Yes, thank you. I think I said QB, but I wrote QB. Like this. Now I have two disjunctions, which means I have to branch 2 times, and there will be 4 branches in the end. I will skip a step, and so there are 4 branches. You can do it in 2 steps or in 1 step. I'm just going to say, let's pick one of the branches where I have PA, and also PB, and also not P, no, sorry. I have PB, no. I want to end up in a branch that doesn't close. So to get a branch that doesn't close, I should pick QA from the first formula. I should pick PB from the second formula. I should pick not, well, I have nothing more to pick because not PA stays and not QB also stays. Yeah, now I'm down to the level of, well, they're not quite literals because they are predicates applied to a constant, but I can't decompose this any further. This branch doesn't close, it's actually open. And there's, I think this is the only open branch, the other 3 close. This means I have found an interpretation for which